Hello everyone, today we will be presenting our overall project where we design and analyze the performance of a complete solar photovoltaic power conversion system and simulated it using MATLAB Simulator. In this project, we designed the PV panel configuration, the DC-DC boost converter with MPPT control, and the single-phase DC-AC inverter. All these components were then integrated and tested through simulation to verify their performance. To give a clear picture of how the system works, the process starts at PV panel, where the sunlight is converted into DC electricity. The MPPT controller then ensures the panel operates at its maximum power point. Next, the DC-DC boost converter increases the PV voltage from around 79.6 volts to 350 volts. This boosted voltage is stabilized by the DC link capacitor before being supplied to the inverter. Finally, the DC-AC inverter converts the 350 volt DC into a clean 230 volts RMS 50 Hz AC output suitable for typical household load. This flow summarizes the entire project from system design to simulation, demonstrating how solar energy is efficiently processed and converted into usable AC power.
Our goal for this project is to power the standard Malaysian household, consuming about 10 kilowatt hours per day. For this, we built a 3000 watt peak solar array. This array consists of 8 high efficiency monocrystalline panels. These panels are configured in 4 parallel strings of 2 panels in series. This gives us a safe open circuit voltage of 95.2 volts, which is under the 120 volt Malaysian standard, and the array current is 37.7 amps, which is for component sizing. Now we move on to system sizing. Accounting for system losses, the daily energy requirement came up to 11.7 kilowatts. Assuming the system gets 4.5 hours of sun, the PV power requirement came up to 2.6 kilowatts, but the system was sized at 3 kilowatts, accounting for a 15% safety margin. This requires 8 panels of 375 watt capacity to power. Finally, for storage, we selected a 48 volt 650 amp hour battery sized for 2 days of autonomy, and then a 60 amp charge controller along with a 5.5 kilowatt inverter was selected to handle peak system loads.
Okay, so let's move on to DC-DC boost converter. As we can see in the slide, we have the V in equals to 79.6 volt and we want our V naught equals to 350 volt. As we want to increase the output voltage level, we need to use the boost converter as it's simple, low cost and also suitable for PV applications. This is the calculation for DC boost converter. So as we can see, we have to find the duty cycle first, which is equal to 0.7726, which is quite high but still suitable for the operation. Next, we need to find the input and output current, and after that, we need to find the inductor value. As we can see, our inductor value is bigger than L critical, which is make sure that the converter is operate in the CCM mode, continuous conduction mode, and after that we can find the capacitor value. Our capacitor value is as stated in the slide, and also next we have to find the LC filter, and after finding all the parameters that we require for DC-DC boost converter, we can insert it into the MATLAB simulation. This is the DC-DC boost converter in the MATLAB simulation. We're using all the parameters that we calculated before, and the one that I circle, which is stated is as boost, is the one that we connect it to the MPPT function, which is I will explain in the next slide. In this DC-DC boost converter, we also use the MPPT algorithm implementation. What is MPPT? MPPT is used to ensure the PV operates at its maximum point under all conditions. So in this project, we implement the perturb and observe P&O method, which adjusts the duty cycle based on the power changes to track the MPPT. This is the MPPT P&O in the MATLAB simulation. So in the MATLAB function block that is code inside it, what it do is the PV voltage and current are read and the power is calculated. Then the P&O algorithm compares the current and previous power to decide the new duty cycle. So the duty cycle output from the MPPT block is sent to the S-boost input of the S-boost converter. So the S-boost signal then control the MOSFET switching, adjusting the converter input, and also this allow the PV system to operate near to the maximum power point.
Now I will briefly explain the key calculation involved in designing DC-AC inverter for our solar PV system. First, the inverter converts a 350 volt DC input into a 230 volts RMS AC output. To achieve this, we calculated the peak output voltage to be 325 volts based on the RMS to peak relationship shown on the slide. This ensures that the inverter can generate the correct sine wave amplitude at the load. Next, we determine the modulation index, which indicates how much of the DC link voltage is used to form the AC waveform. By dividing the peak voltage by 350 volts, we obtain a modulation index of 0.93. So this keeps the inverter operating in the linear SPWM region and avoids waveform distortion. For the output current, we use the rated power of 5.5 kilowatts and 230 volt output to calculate about 24 ampere RMS. This value matches what we observed in the simulation, confirming that the inverter delivers the expected current. We also calculated the load resistance to be 9.62 ohms, which ensures that the inverter is tested under full load conditions. For the LC filter, the inductor value of 2 mH helps reduce high-frequency ripples, while the capacitor value of 3.17 microfarads, rounded to a standard 3.3 microfarad, helps smooth the waveform into a clean sine wave. Finally, we selected switch rating of at least 600 volt and 40 ampere to safely handle transients and current spikes, and we added a 2 microsecond dead time to prevent shoot-through between switching devices. This calculation together ensure that the inverter operates safely, efficiently, and also generate a clean AC
I
output.
think the overall PV array system simulation using MATLAB Simulink. So our system is using the MPPT, which is the PNO method. So here is the overall coding of the MPPT PNO method. So then let's jump off to the each of the subsystem. So first is the PV array subsystem. So here is the PV array subsystem, and below is the scope. So here you can see the output of the PV array subsystem. So you can see first is the irradiance, PV voltage, PV current, and also the PV power. And the next subsystem is the DC-DC boost converter. So here is the DC-DC boost converter subsystem, and below is the scope. So here you can see the output of it. So you can see the input voltage, input current, output voltage, and also the output current for the DC-DC boost converter. And last but not least, the DCAC inverter subsystem. So here it is, and also below is the scope. So now you can see the output of the DC-AC inverter. So you can see the output voltage, output current, input voltage, and also the input current for the DC-AC inverter. So that's all from me. Thank you.
Our design was validated through simulation. The array voltage was simulated at 79 volts, which is only 1% deviation from our predicted 79.6 volts. The array current was 38 amps, which is also within 1% of our 37.7 amp calculation. Most importantly, the power was simulated at 2993 watts, which is a mere 0.23% deviation from our target 3000 watts. Finally, this close match between the predicted and calculated values shows that our design is performing as expected.
The input voltage stays around 78 to 80 volt, very close to the theoretical 79.6 volt, showing that the MPPT keeps the PV array near its optimal point. Then the output voltage settles smoothly at about 344 volt, which is slightly below the 35 volt target due to the normal switching loss. Then the input current has a short startup transient, then stabilized around 4.9 A, which is close to the theoretical 4.71 A. This indicates that PV is delivering power near its maximum point. And also, the output current is steady with a small ripple around 1.046 A, matching expected boost converter behavior. Overall, the simulation aligns well with theory, confirming proper boost operation and also effective MPPT tracking.
For the inverter simulation, our theoretical output current was 23.91 ampere RMS. In Simulink, we measured around 24 to 25 ampere instantaneous, which is normal because the cursor reads the waveform at a single point rather than the RMS value. The LC filter also introduced a small voltage drop, and the modulation index of 0.93 slightly affects the amplitude, causing minor differences between theory and simulation. Overall, the result matched very closely. The LC filter effectively removed the 20 kHz switching harmonics, and the inverter produced a clean 50 Hz sinusoidal currents. This confirmed that our inverter design performed as expected and can reliably deliver the rated 5.5 kilowatts.
So moving on to the next slide, we analyze the system performance under irradiance variation, which is the primary environmental disturbance on a PV system. So we tested the full system under three conditions, which is 500, 1000, and 1500 irradiance. Looking at the LC output voltage waveform in the slides, so the results are clear. So the peak voltage achieved at 500 irradiance is the lowest, and it scales up as the irradiance increases to 1000 and also 1500 irradiance. So this analysis confirms that the output of our power electronic system is directly proportional to the available solar resource. Higher sunlight intensity results in a higher overall output voltage, or VRMS, and validating that the MPPT and inverter stages handle variable input power predictably and stably.
Meanwhile, for the load variation analysis, we tested the inverter under 4 different load values: 1 ohm, 10 ohm, 100 ohm, and also 1000 ohm. This main observation is that the output voltage increases as the load resistance becomes higher. This happens because lighter load draw less current, which reduce voltage drop across the inverter switches and the LC filter. As a result, the inverter is able to maintain a higher output voltage. In contrast, heavier load draw more current, creating larger voltage drop and causing the output voltage to be slightly lower. Overall, the inverter remains stable across all load conditions and the system performed as expected. In conclusion, our solar photovoltaic system was successfully designed and simulated in MATLAB Simulink, and all project objectives were achieved. The pivot array model showed less than 1% deviation from theoretical values, confirming accurate modeling under different conditions. The DC-DC boost converter, together with the MPPT controller, operate effectively, maintaining the PV voltage near its maximum power point and delivering a stable 350 volt output. The inverter also performed well, producing a clean 230 volt RMS, 50 Hz AC output with proper filtering. When tested under variation in irradiation, switching frequency, and load, the system remained stable and behaved as expected. Overall, the complete PV to AC conversion system shows strong potential for residential application. That's all from us. Thank you.